Welcome back. We're going to make one more tweak to our derivative definition. Rather than using a to represent the point of tangency, a is a very specific kind of number. Usually it's used for, or letter, it's used for constants, like 1, or in our example, or 5, or whatever. Instead of using a, we're going to use x. And in this way, we're making a subtle shift from the derivative being something that gives you values, like some specific values, like we saw -2 in one of our examples recently, into the derivative being a function of x. So all it is, it's exactly the same definition, it's just that the a's have been replaced with x. So we have the limit as the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the definition of the derivative that we're going to mostly be going to. A couple of terms that you might hear when talking about the derivative. We would say that f is differentiable. At x, if the derivative of f at x exists, so if f prime of x exists. And differentiation is the process of calculating the derivative. Differentiation. So you might hear instructions asking you to differentiate the function. Or something asking you, is this function differentiable? Does it have a derivative? So all the directions below are the same. Differentiate f of x equals x squared, or find the derivative of f of x equals x squared, or find f prime of x when f of x equals x squared. Those are all the same. Find the slope of the tangent line of f of x equals x squared. Find the instantaneous rate of change of f of x equals x squared. All 5 of these are asking you exactly the same question. They're just using different words and different concepts of the derivative to ask them. So here in example 3, we're asked to find the derivative of f of x equals x cubed using the limit definition. Now this limit definition is the first step that we're going to take. We're going to write out the limit definition. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is the limit definition of the derivative. Now our first step is going to be to plug in x plus h into plug the x plus h into the function, where in this case the function is x cubed. So we're going to replace the x with x plus h. And then f of x we just copy down. This is x cubed. And sometimes this throws people off, so let me just take a moment to do something off to the side. So if you have like f of x equals x cubed here, well, f of 5 would be 5 cubed. Let me just write out some things here. Okay, so f of 5 would be 5 cubed. So all you do is you replace the x here with 5s. And in the same way, if you have f of x plus h, which is just some other thing inside of here, you're going to replace the x with x plus h. Now to make sure that the x plus h is packaged together, we're going to put little parentheses around it, and then we'll have the cube. So all we're doing is we're just replacing the x in our function definition with x plus h. That's what it means to plug something into a function. You just replace all the inputs with what you're inputting. It just may seem a little strange because we have this x here and then this x here with a plus h now, but just think about replacement. It's like you're taking the x and swapping it out for an x plus h, and then take this x, swap it out for an x plus h. So now we're at this stage. Now what we're going to do is try to expand out the top and simplify, and the hope is that we'll take this limit, which is an indeterminate limit. It's a 0 over 0 type of limit. Remember, we talked about that just a moment ago. And we are going to try to cancel off the factor that's making the top and the bottom 0. And it's always this factor of h. This is the one that's causing the top and the bottom to both be 0. So somewhere after we simplify the top, we're going to get a factor of h that will cancel with this factor of h. Now when you're taking x plus h cubed, what you can do is just take x plus h times x plus h, work that out, and then multiply by another x plus h. So you'd have a bunch of polynomials to multiply. Or if you remember the binomial theorem, which raises binomials to high powers, this was at the tail end of pre-calculus if you took pre-calculus at Mount Sac, then you know how this expands. This is going to expand as x cubed plus 3 times, and then x goes down a power, h goes up a power, and then 3 times x goes down a power, h goes up a power, and then x goes down a power, and then h goes up to the power of 3. And these coefficients you can get by Pascal's triangle, or you can get by the binomial coefficients. 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And if you don't remember that part of it, don't worry about it too much for now. Just remember that you can multiply all this stuff out either the long way, or you can go back and review the binomial theorem to help you out. Then you have this minus x cubed to copy down. Here the x cubes are going to cancel. And we've got 3x squared h plus 3x h squared plus h cubed all over h. Now at this point we can either factor out the h and then cancel the factor of h on top and bottom, or just divide each of these 3 terms by h. One other thing to note is that I'm continuing to write the limit as h approaches 0. We haven't yet plugged in h equals 0. We haven't taken the limit. We still have h's, in other words. I was trying to come up with a bad pun about this problem is taking h's. All right, so here we're going to now take the limit as h approaches 0, which means plugging it in, and notice that we're doing it for h. It's h that's approaching 0. X is some other variable that's not affected by this limit. This limit is only taking h to 0. It's not taking x anywhere. So the 3x squared is just 3x squared. Then we have plus 3x times 0, which is going to be 0, and then 0 squared, which is going to be 0. So in the end, we just get 3x squared, which seems a little bit funny because we're used to getting numbers at the end of this process. But remember, we're making this subtle shift from specific values of the derivative into the derivative as a function of x. So when we're trying to find f prime of x, we hope at the end to have a function of x. Now, if we don't have a function of x and we just have like 5, well, that still could be a function of x. It could just be a constant function. But a lot of times we'll have these variables x in there, and that'll be okay. That's expected. So that's what the derivative of x cubed is with respect to x. It's 3x squared. So if you wanted to get the slope of the tangent line of x cubed at, let's say, x equals 2, well, that's pretty straightforward. You just plug in x equals 2 to the derivative that we just found, and you'll get 3 times 2 squared, so that'll be 2 squared would be 4, times 3 is 12, so that would be a slope of 12. The slope of the tangent line at x equals 2 would be 12. So this gives us a formula for finding the derivative, or in other words, finding the slope of the tangent line, or in other words, finding the instantaneous rate of change of our function x cubed at any given x value. And that's pretty nice, in my opinion. So moving on to example 4. We have another find the derivative of f of x equals, and using the limit definition. And in this case, f of x is now a rational function. It's x over x minus 3. Well, we're going to start it the same way. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. This is the limit definition. If you see find the derivative using the limit definition, this is it. And so the first step that you'll always want to take is write out that limit definition, and that's exactly what we've written right here. This is the limit definition. This is one to commit to memory, although we've explained how you can visualize this, so that can help your memory a lot better. Like you can think of the top of the fraction as the rise. You can think of the bottom of the fraction as the run. So if you have a visual picture of this, then it makes it much easier to remember this definition. And you're taking h to 0 because you're shrinking that interval of x, or t if you're talking about time. All right, so let's jump into plugging in x plus h into the function. Now remember that every single x gets replaced with an x plus h. So this will turn into x plus h over, and then this x gets replaced with an x plus h, and then we copy down the minus 3. A lot of times I'll see a student writing the function with a plus h on the side. That would be the case if we had f of x and then plus h to the side, like so outside of the function. But when the plus h is inside the parentheses, that means it goes in with the input. It just travels along with the input. So wherever the x's are, that's the row representing the input, that's where the x plus h's are going to go. So the plus h doesn't go to the side of the function, it goes in there with the x's. So then you have minus f of x. Here it's a copy and paste. Control C, Control V. You can tell I'm a Windows user. And now we're trying again to cancel off this factor of h that's causing the bottom to be 0. So how are we going to do it? Well, one way is to simplify the top by clearing out these little fractions. And the way we can do that is multiply the top and the bottom of the big fraction by the LCD of the little fractions, the least common denominator of the little fractions, which will be x plus h minus 3 times x minus 3. It's just the product of these two denominators. So then you want to make sure to do the same thing to the bottom, so you're not actually changing the fraction. As long as you scale up the top and the bottom, like multiply the top and the bottom of the fraction by 2, then you haven't changed the value of the fraction overall. So this LCD is going to distribute to the first fraction and cancel off the x plus h minus 3's. Those will cancel. And we'll have the x plus h that's left over from the top, as well as the x minus 3 that's left over that wasn't canceled. So when this distributes, just draw little arrows to remember this is going to distribute to the first term and the second term. So when it does it to the first term, the x plus h minus 3's cancel, and you have x plus h times x minus 3. And to the second term, we're going to have the x left over for sure. There's nothing canceling that off. The x minus 3's will cancel, and we'll be left over with the x plus h minus 3. Now in the bottom, our goal is to cancel off that factor of h. So we want to leave the bottom factored. We don't want to mess things up and just start distributing everything. We could distribute these two, but that's really an unnecessary step. Our goal is to cancel off that factor of h. That's our primary goal. Now the top is not factored, and there isn't a factor of h in each of these terms, so we're just going to have to expand everything out and hope that after we simplify, we'll have a factor of h. So we're going to do a FOIL for the x plus h times x minus 3. And then distribute the negative x. So we have negative x squared minus xh plus 3x. Again, not distributing on the bottom because we want to cancel off that factor of h. We want to leave it factored. Now on the top we're going to have a big canceling fest. Let's see. Oh, negative 3x, positive 3x. Oh, x squared, xh, xh. It's kind of fun, actually. And then after the dust clears on the top, we have negative 3h. There's our factor of h that we need to cancel off with the h on the bottom. So things are looking great. And we'll cancel off that h now. When you're canceling that h, it's like you're dividing the top and the bottom of the fraction by h. That's scaling the fraction down. It's nice to be able to think of fractions in many different ways. Okay, now that the factor of h has been canceled, now that 0 over 0 problem is gone. So now we can take the limit as h approaches 0 and take that limit by plugging in h equals 0. So at this point, we don't have to write the limit anymore because we're replacing h with 0. Now in the bottom we're going to get x minus 3 times x minus 3, which gives us x minus 3 squared. That would be a nice simplified way of writing our result. So once again, what we have is the derivative of this function, in other words, the slope of the tangent line of this function, written as a function of x. So if we want the slope of the tangent line at any x value, we just plug it in and we'll get the slope of the tangent line there. Now, of course, we couldn't plug in 3, but then again, 3 is not defined. The function is not defined at x equals 3. So that kind of makes sense right there. All right. So following up with that same function, we're asked, what is the slope of the tangent line to the curve y equals x over x minus 3 at x equals 2? So same function. And we just found the derivative of the function, which is the slope of the tangent line. So all we have to do is plug in 2 to the derivative that we just found, and that will give us the slope of the tangent line at x equals 2. On the bottom we'll have negative 1 squared, which is positive 1, and then negative 3 divided by 1 is negative 3. Find the rate at which f of x equals x over x minus 3, same function, is changing with respect to x at x equals 2. Same x value that we just found a moment ago. Well, that's just going to be negative 3. We already did all the work for that. Okay, let's take a look at example 5. Here we have the same directions, but a different function. Find the derivative of f of x equals the square root of x squared plus 1 using the limit definition. Our first job, write out the limit definition. You'll get points for doing so. At least a point maybe. F prime of x equals, the limit as h approaches 0, of f of x plus h minus f of x over h. All right, so now we're going to take x plus h, plug it into the function, and we'll get x plus h squared plus 1. That's what it looks like to plug in, to replace the x with an x plus h. It's all about replacement. And then copying the function for f of x down. Now, once again, we don't have a factor of h to cancel this one on the bottom, so we're going to have to do some algebra work to figure this out. When you see the radical, what do you think about as one possible algebraic strategy? If you said conjugate, yeah, let's give it a try. So we're going to multiply the top and the bottom of the fraction by the conjugate of the top. The great thing about the conjugate that helps out, especially if we have two radicals, So these two radicals, or two terms, are both radicals. The great thing about the conjugate is that it's going to get rid of those radicals. When you distribute, the first term times the first term will get rid of the radical, because you'll get that radical squared, which gets rid of the radical. And then you'll have the last terms multiplied to each other. And that's, again, going to involve the radical squared, which is going to undo the radical. So by multiplying the top by the conjugate, you bring everything out of the radicals and out where you can then hopefully combine them together and start canceling and simplifying. On the bottom, we don't want to do anything because we want to leave that factor of h there and until we can cancel it. Oops. Notice that I put the parentheses around the x squared plus 1. This is, again, another place where there's a common mistake that's made where you forget to put the parentheses, and then instead of subtracting the entire result of multiplying these two radicals together, you're only subtracting the first term. And that's not really what we want. We want to subtract the entire result of multiplying this radical by this radical. And that entire result is the x squared plus 1. So we gotta have to put that entire result in parentheses to make sure we're packaging that together. And that we're subtracting that whole thing right there, not just the first term. If we just had minus x squared plus 1, that would be subtracting the first term, but not the second term. And that's not what we want. Now on the bottom, we're gonna leave everything factored. In fact, I'm not even going to bother to expand out the x plus h squared. Later, we're going to be plugging in h equals 0. If everything goes right, we're going to plug in the h equals 0, and it will. It'll go right. And so there's not really a need to expand this out at this point. Now we do have a need to expand on the top though, because we want to simplify the top so we can get a factor of h to cancel off this factor of h. So we'll expand the binomial. We'll distribute the negative. Leave the bottom alone. All right. A lot of writing, but you get used to it. And have a big canceling fest. X squared cancels with x squared. 1 cancels with 1. Well, maybe that wasn't a big canceling fest, but it was a medium-sized one. Now at this point, let's factor out that h. We'll factor it out officially. Now that it's factored, we can cancel it off. Now the 0 over 0 problem is gone. So we have the limit as h approaches 0 of 2x plus h over square root of x plus h squared plus 1 plus the square root of x squared plus 1. Okay, so now at this point we can plug in h equals 0. And we'll have 2x left on top over the square root of x squared plus 1 plus another square root of x squared plus 1, which is 2 the square root of x squared plus 1. And as a last step of simplification, we can get rid of the 2's, and we have x over the square root of x squared plus 1. Whew, that one involved a lot of writing. Now we'll take this a step further and find the tangent line to that same function, to the curve of that same function at x equals 1. Well, that just involves taking the derivative and plugging 1 in. So we get 1 over the square root of 1 squared plus 1, which is 1 over the square root of 2. And actually, I didn't read this carefully enough, and so maybe this is a good example for you. It said find the tangent line. It actually didn't say find the slope of the tangent line. If we were asking for the slope of the tangent line, that's what we found right here. This was the slope of the tangent line. But we want the tangent line, so implicitly what's being asked here is find the equation for the tangent line. So there's the slope of the tangent line. Let's get a point on the tangent line. We have the x value, we just need the y value. How can we get the y value? Plug that x value back into the original equation, which was the square root of x squared plus 1. So here we're going to get the square root of 2. So then the equation is going to be, using point slope form, y minus y1 equals the slope times x minus x1. No need to rationalize the denominator, although if you did, it would be square root of 2 over 2. You can write it that way as well. A couple more things at the bottom of this page. One is that there are many ways to write the derivative. We've seen some of them, f prime of x. There's also y prime. So if you have like y equals x cubed, then you can write y prime equals 3x squared. We did that derivative in one of our examples. There's also this notation that looks a little funny at the beginning, dy over dx. But if you think about it, it's reminiscent of the delta y over delta x that we saw before. Delta y over delta x was calculating the average rate of change of a function, whereas dy dx is calculating the instantaneous rate of change of the function. So if you think about dy dx, that one gets closer and closer to, or approaches delta y delta x approaches dy dx in the limit as the delta x's are shrinking down to 0. Now the dy and the dx, technically, when you're talking about derivatives, don't really stand for things. These aren't really like separate things, but as we'll see in a future packet, there is a useful way of treating these as separate variables, where here dy you can think of as like the rise along the tangent line, and dx you can think of like the run along the tangent line. But we'll get there later. For now, just consider it to be a single package. So dy dx is a single package that represents the derivative of y with respect to x, or in other words, the slope of the tangent line. This notation, by the way, is called Leibniz Notation, after one of the two founders of calculus, Mr. Leibniz. You can also use Leibniz Notation with functions, so you can say df dx. You can also write Leibniz Notation with functions in this way, so d dx of f of x. Here, this is helpful if you want to have something more complicated that you're taking the derivative of, so you write whatever the function is over here on the right side, and then in front of it you just put this d over dx. And this is like an action that's going to happen on this function. Kind of like you write the limit to the left and then you write the function to the right. It's the same kind of idea. Sometimes you'll see a big D for derivative, and so big D of f of x just represents the derivative of f of x. Or you might see d with a subscript of x that says take the derivative with respect to x of this function f of x. These last two are less common, but you might see them in some other books. Now, it'll be important to know Leibniz notation was something we're definitely going to see a lot of, though, so that's going to be important to become familiar with and comfortable with. So here's what it looks like to plug a value into a derivative. With the prime notation, it's just f prime of 2. We've already seen that before, like f prime of 1, f prime of 2. With Leibniz notation, it's a little trickier. The way you write it is dy dx, and then you put this vertical bar, which means evaluated at, x equals 2. So this would take x equals 2 and plug it into dy dx. So there's a little bit of notation for you. Thanks for watching this part, and see you in the next part.